Okay, so I decided to switch formats a little bit for this video of section 2.8 because what we want to focus on in this section is some of the graphical interpretations of the derivative. So graphical derivative. Okay, so suppose that I have a function here. I'll just draw something with a few curves in it, something like that maybe. Okay, and suppose that, so this is my function f of x. And what I would like to do is maybe right underneath, I'll draw a graph of the derivative, f prime of x, with x. Okay, now we actually already know how to do this slightly, I should say, because we know that where the original function is increasing, we know that the derivative is above the x-axis, and where the function is decreasing, we know that the function is below the x-axis. So therefore, where we have a little bit of a plateau here, we're going to have zero slope. We're going to have zero slope there, zero slope there, zero slope there, zero slope there. And so I like to start with the places where the slope is zero. So let's go ahead and write those in. This is going to be zero here, zero here, zero here, and zero here. Very good. Now, in this region, what's happening is that we have a positive slope, and that slope is going to 0. So we have a positive slope that's going to 0. Okay, for the derivative. Excuse me. And then in this region, the slope is going from 0 to slightly negative, maybe -1, and then goes back to 0. So the curve comes down to maybe -1. This is kind of like where the maximum negative is. Then it comes back up to 0. Okay. Similarly, we have the same kind of idea here. We're going from 0 to maybe a +1 slope. We're just kind of eyeballing it. So it's coming up to about here, and then we're going back down to 0. Okay. And then finally, this one, that looks steeper than 1, steeper than -1, maybe -2, again, we're just eyeballing it. But then we're coming back to 0 again here, so we would stop about there maybe. Okay, and then finally, we come back up to 0. And what's happening here, the function is increasing all the time, so our derivative is just going to be positive. Good. Perfect. So this is your graph of the derivative function. So notice again how we started that. We started with the zeros, and then we filled in the other places. Good. Okay, so we haven't talked much about when a function might fail to be differentiable or fail to have a derivative. And so here's an example where we might have trouble. Suppose I've got a function that looks like a v. You may recognize that as an absolute value. It's off the origin though. Just for fun, I put it away from the usual spot. But the idea here is that if you were to try to draw the derivative, so this is your function f of x, and we're drawing the f prime of x. What you're looking at here is the local slopes, right? And it looks like the local slopes here don't change. So the local slopes here are about 1. And so up to this point, the local slopes are going to stay equal to 1. And then something happens at this point, right? Because suddenly the slopes change from a +1 slope to about a -1 slope, approximately. And so we're going to be jumping from a +1 slope down to a -1 slope, like that, right? And so in this case, the function is going to fail to have a derivative right there at that point. So let's write that down. A function will fail to have a derivative at sharp points of the graph. But heard a ding. Something must be done. Sharp points of the graph. Okay, so in this case, the function, we would say that the function is differentiable, meaning it has a derivative everywhere except the single point, right? So here the function fails to be differentiable at the single point. Good. All right, so otherwise, in this case, for example, f is differentiable, that's a long word, everywhere. Okay, so let's take a look to see how this works algebraically. How would you fail to have a derivative algebraically? So let's take a look at the, we said this was like an absolute value function. Let's actually take a look at the absolute value function. So how about let f of x be equal to the absolute value of x, and that does have your normal V shape, right? Oops. And from the graph, you know what's coming, right? But let's see if we can show that algebraically. So we're going to take, let's see, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h, which in this case will be the absolute value of x plus h minus the absolute value of x divided by h. Good. Now, the problem point is going to be at 0, so we don't really need to, we know that if we stay away from 0, we are going to be able to compute the derivative. It's either going to be a -1 or +1. So let's go ahead and be more specific and compute the derivative at 0 just to see what happens here. So that's going to be 0 plus h minus 0 divided by h. And so that's going to be the limit as h goes to 0 of the absolute value of h divided by h. What's that going to be? Well, if h is greater than 0, the absolute value of h is just h. And in that case, then the limit as h comes to 0 from the right is going to be, you can simplify it to just h over h using the simplification, which is 1. And that's what you see up here. We're saying that as we come in from this side, the local slopes are equal to +1. And what's going to happen if I come in from the negative side? I have to replace the absolute value with minus h, right? And so do you see what's coming? As we come in from the left, that's going to be minus h over h, which is -1. Okay, and those are -1. Good. So therefore, the limits do not equal each other as you come in from the right or the left. Therefore, the limit at 0, f prime of 0 does not exist as a limit, right? The limit depends on which direction you're coming from. And so that's why geometrically, right, a function that has a sharp point is not going to be differentiable at that point, meaning that the derivative will fail to exist. Okay, so I'm going to stop this video here, and in the next video we'll look at more examples.